In this recording, I'll be going through the review for Test 4, and that covers chapters 11 and 12. So let's go ahead and get started. So here we're just filling in the blanks with some key terminology that you should be familiar with. On number 1, it's probability. That's a measure of how likely an event is to occur. An experiment is any occurrence for which the outcome is uncertain. For example, when you roll a die, you don't know what the outcome is going to be, and so that would be an example of an experiment. And number 3, it says when you flip a coin, getting heads or tails are called the possible outcomes. The set of all possible outcomes of an experiment is called the sample space. On number 5, it says probabilities have a value between what two numbers? That would be 0 and 1. A probability of 0 means that it's impossible for something to occur. The probability of something equaling 1 would mean that it's certain to occur. And anything in between, like a probability of 1/2, is anything in between would be a way to measure most probabilities. On number 6, it says the probability of E is equal to the number of favorable outcomes, and it should be divided by the total number of outcomes. Number 7, the ratio of unfavorable to favorable outcomes gives the odds against event occurring. And this is the most common way that we express odds. Most of the time that's how you'll see them, as odds against. If you have odds in favor, then we would reverse the ratio. It would be favorable to unfavorable outcomes. And again, we use a colon usually when we measure odds. On number 8, it says, what's the difference between a theoretical probability and an empirical probability? So a theoretical probability is based on a study of the possible outcomes. So like when you roll a die, you know that you have an equal chance of getting a 1, 2, 3, 4, 5, or 6. And so we know that the probability of getting a 6, for example, is 1/6 based on looking at the possible outcomes. Empirical probability, which is sometimes referred to as a relative frequency probability, is based on observation or collected data. Probably the best example, every day we are concerned about the weather, and weather forecasts are based on observation of the current weather conditions and basically experience from the past, from data that's been collected in the past. So that would be an example of empirical probability. In number 9, it says a first experiment can be performed in m distinct or different ways, and a second experiment can be performed in n distinct ways. Then the two experiments in that specific order can be counted in how many ways, and what we found is you just multiply the two. And so the next two problems are examples of this. It says a frozen yogurt shop offers 8 flavors and 12 toppings. How many ways of choosing one flavor and one topping are there? Well, let's see. There's 8 flavors to choose from. There's 12 toppings, and we multiply the two numbers, and that tells us there's 96 ways to choose one flavor and one topping. In number 11, it says a restaurant offers a dinner special where you have a choice of 2 salads, 6 entrees, and 4 desserts for one low price. In how many ways can you choose your dinner, assuming you have a salad, an entree, and a dessert? Well, we know there's 2 ways to choose our salad, 6 ways to choose our entrees, and 4 ways to choose dessert. So this is just like the case where you have 2 choices to make. Here we have 3. we're just going to multiply all those numbers and we get 48 ways. All right, let's move to the next slide. It says, suppose you have a bike lock with 4 dials. Each has 10 letters on it. In how many ways can you choose a combination for the lock? Well, notice you're making 4 decisions here. Each dial has 10 letters on it, so you're choosing from 10 items. And so there's 10 ways to make each of these choices. And so we're going to multiply those numbers. We get 10 to the 4th. So there's going to be 10,000 ways to choose a combination for the lock. Now I would encourage you to try number 13 before you watch the video. In fact, I would say that's true for all these problems. These are all review of things that we've done in this chapter and these 2 chapters. And then watch the video. At least that's what I would recommend. So here in number 13, you have a 6-character license plate where you're going to have 3 letters of the alphabet followed by 3 numerical digits. How many different license plates are possible? So we have 3 choices for the first 3 characters. We're going to be choosing letters. And for the last 3, we're going to be choosing digits. Well, when you choose a letter, you have 26 letters to choose from, since there's 26 letters in the alphabet. And so there's 26 choices for each of these. Notice they didn't have any restrictions for us, so it's not like we couldn't choose certain letters. And the same thing's true with digits, except for we have 10 of those, 0 through 9. And so there's 10 choices for each of those digits. And we want to multiply all those numbers together. We get 26 cubed times 10 cubed, and I'd throw that in the calculator. You get 17,576,000 ways. All right, at number 14, it says, of 48 students surveyed at Brookhaven College, 20 had a pet at home. Based on these findings, so basically based on this data, what is the probability that a student at Brookhaven College has a pet at home? Well, let's see. There's a total of 48 students, and 20 out of the 48 have pets at home. So if we're going to find the probability that you have a pet at home based on this data, it would be 20 out of 48, which reduces to 5/12. Now, I would say you might argue that 48 students is not enough to make some kind of generalization here, or to find an accurate probability. But in any case, this is how you would do it. In number 15, it says the number of men and women wearing hats at a recent baseball game is recorded. The results are shown to the right. If one of these people are selected at random, determine the probability A, that the person is a woman. Well, let's see. There's a total of 42 women out of 98 total people. And when you reduce that, you get 3/7. And I would just remind you that you should be able to reduce fractions. If you need your calculator to help check your answer, I would encourage you to do that. But you should always give your probabilities when you're writing them as a fraction with reduced answers. In part B, it says the person is a man wearing a hat. So our total is going to be the number of men. Let's see. Actually, the person is a man wearing a hat. It does say if one of these people are selected at random. So we're still picking from all the people here. So our denominator is still 98. A person being a man wearing a hat, well, there's 35 of those. So it's 35 out of 98, which does reduce to 5/14. And in 16, it asks what kind of probability are we doing here in 14 and 15. These are empirical probabilities, which are based on collected data or what we've observed over time. And so we'd say empirical probability, or again, you could call this a relative frequency probability. All right, let's move on to the next page. So on number 17, it says one card is selected at random from a deck of cards. We'll just say it's been shuffled really well. Find the probability, or find each of the following probabilities. So first of all, we need to find the probability of getting a king. Well, there's 4 kings in a card deck out of a total of 52 cards, and so that would reduce to 1/13. Now the probability that you don't get a king, well, if there's 4 kings, that means there's 48 cards that are not kings, and that reduces to 12/13. Now you could have just written 12/13 right away, just remembering that the probability that an event occurs plus the probability that an event doesn't occur should always equal 1. And notice 1/13 plus 12/13 does equal 1. In letter C, we need to find the probability of getting a club. Now remember, clubs is one of the 4 suits in a deck. You have clubs, spades, hearts, and diamonds. And there's 13 of each, so there's 13 clubs in a deck of 52 cards, which reduces to 1/4, which makes sense if there's 4 suits and the same number of cards in each suit. Each suit is 1/4 of the deck. Now in letter D, it says, what's the probability of getting a red card? Well, we know that we know that the diamonds and the hearts in a card deck are red. That's half the cards, or 26 out of 52 cards, which reduces to a half. And again, that makes sense. Half the deck is going to be red, half the deck will be black. What's the probability of getting an ace or a king? Well, remember, probabilities are the number of favorable outcomes divided by total outcomes. There's 8 favorable outcomes here. There's 4 aces and 4 kings out of 52. And so you have a 2 in 13 chance of getting an ace or a king when you draw 1 card. In number 18, it says a coin is tossed and a die is thrown. Find the probability of getting a tail and a 3. Now, this is an AND probability, and there's 2 cases when we deal with AND probabilities. In this case, tossing a coin has no effect on the probability when you throw a die. And so these are what you call independent events. And so all we need to do is find the 2 probabilities and multiply them together. And so the probability of getting a tail is 1/2. The probability of getting a 3 when a die is rolled is 1/6. And so when you multiply, you can see that the probability you get a tail when you flip the coin and then get a 3 when you roll a die is 1 in 12. On number 19, it says, if a young married couple intends to have 4 children, find the probability that they will have 4 girls. Now, throughout this, throughout the section on probability, the chapter on probability, we did this kind of problem 2 ways. One way is you could actually write out all the different possible outcomes when you have 4 children. And we would call that the sample space. And based on the sample space, you can figure out what the probability would be that you have 4 girls. In this case, I'm going to do it the other way that we learned. These events, each time you have a child, that's got an uncertain outcome. So each time is considered an experiment, and it's occurring 4 times. And each time, whatever child you had the first time, boy or girl, has no effect on what you're going to have the next time. And so these are also considered independent events, having a girl, that is. And so the probability of getting a girl and a girl and a girl and a girl is just going to be the probability of having a girl times itself 4 times, Each time you have a 1 in 2 chance of having a girl, and when you multiply across, you get 1 over 16. So 1 in 16 chance that you'll have 4 girls, assuming you have 4 children. All right, now in number 20, it says there are 4 red marbles, 5 yellow marbles, and 3 blue marbles in a bag. Determine the probability of drawing a red one from the bag. So if you're just drawing one marble, that's what's happening here. We're just drawing from the bag, and we want to know what the probability is drawing a red marble. Well, there's 4 red marbles, so probability of getting red, I'm just going to use R here, is 4 out of, 4 plus 5 plus 3. It's a total of 12 marbles. And so there's a 1 in 3 chance that you're going to get a red. Now notice on B it says find the probability of drawing 2 yellow marbles from the bag without replacement. In other words, when you pull out the first yellow marble, you're not going to put it back before you draw the second marble. So for this reason, the second time you draw a marble, that probability is going to be affected by what happened when you pulled the first marble. There's going to be less marbles to choose from. So these are considered to be dependent events. And so it's going to be just a little bit different. The probability of getting a yellow and then a yellow is going to equal the probability of getting a yellow times the probability of getting a yellow, given that you've already chosen a yellow. So this is the adjustment we have to make for dependent events. So before we said with independent events and probabilities, you just multiply the probabilities. Here, the first time you draw a yellow, it's going to be just like before, but the second time you draw is going to be affected by that first one, and so that's why we had to adjust our probability here. So the probability of getting a yellow the first time, well, let's see, there's 5 yellow marbles out of a total of 12. Now the second time, now we're assuming we already drew a yellow, so there's only 4 yellows left out of a total of 11 marbles since we already chose one. And so 4 and 11 would be the probability that you get a yellow the second time. And so let's go ahead and simplify this. Notice the 4 and 12. 4 is a common factor of 4 and 12. Divide by 4 here you get 1. Divide by 4 here you get 3. And now when we multiply across, we get 5 over 33. All right, in number 21, if you are dealt one card from a standard 52 card deck, notice just one card, what's the probability of drawing an ace or a king? Now, when we deal with OR probabilities, we have to look at whether or not the events are mutually exclusive or not. In other words, is it possible to draw an ace and also a king when you draw one card? Well, of course not. Ace or king, totally separate cards. There's no way you could draw a card that has an ace and a king on it. And so these are considered mutually exclusive. And so the probability for drawing an ace or a king would just be the probability of drawing an ace plus the probability of drawing a king. And so there's 4 kings in a card deck which has 52 cards. And the same thing for the kings. So 4 aces, 4 kings. And so that's a total of 8 out of 52, which reduces to 2 13s. All right, now look at the next problem and see how it's different. What is the probability of drawing an ace or a heart? Is it possible to draw, when you draw one card, to get an ace and also a heart? Well, of course it is. You could get the ace of hearts. And so these are not mutually exclusive events. And so the probability would be set up this way. The probability of getting an ace or a heart is equal to the probability of getting an ace plus the probability of getting a heart. Now keep in mind, in both of these probabilities, we're including the ace of hearts. And so for that reason, we have to subtract out the probability that we get an ace and a heart. And so let's go ahead and finish this out. And this is the general formula for OR probabilities. You could always use this. In fact, if we had used it in A, the probability that we got an ace and a king would be 0, and it wouldn't change anything. So you could always use this formula if you prefer. So the probability of getting an ace is 4 in 52. The probability of getting a heart, remember the hearts is one of 4 suits, and there's 13 in each suit. And then we need to subtract out the probability that you get an ace and a heart. So there's one ace of hearts. And so there's a 1 in 52 chance that you'll get an ace and a heart. And so when we add all that up, we get 16 over 52, which reduces to 4/13. All right, let's look at C now. It says if 2 cards are drawn, so notice this is different. We're not just drawing 1 card, we're drawing 2. Without replacement, which makes sense. Normally when you draw 2 cards, you don't draw one and then put it back and then draw another. You're going to draw 2 cards and you won't replace either card. Well, once you take the first card, you won't put it back. All right, so it says, what is the probability of drawing 2 jacks? So this is an AND probability, the probability of getting a jack and then a jack. Now keep in mind, the question you should ask yourself is, are these dependent or independent events? Will the probability the second time be affected by what happened the first time you drew a jack? And of course it will, because you're going to have, when you draw the second card, you'll have 1 less jack to choose from, because we're assuming we got a jack first time. And you're also going to have less total cards. Instead of 52, it'll be 51. And so this will be like 20b that we did up above. So it's the probability of getting a jack plus times the probability of getting a jack given a jack was already chosen. So the probability of choosing a jack would be 4 in 52. And then the second time, we've already chosen 1 jack, so now there's only 3 to choose from out of 51 cards, since we'd already drawn a card. Now, I'm going to go ahead and simplify these. 4 over 52 reduces to 1/13, and 3 over 51 reduces to 1 over 17. And if we multiply across, we get 1 over 221. All right. Let's go ahead and, I believe this is our last slide on probability, so we'll finish this up. It says the odds against True Colors winning a horse race are 5-2. So we know odds against is the ratio of unfavorable to favorable outcomes. So you can see we have 5 unfavorable outcomes. That's when True Colors doesn't win. 2 favorable outcomes, that's when True Colors does win, which means there's a total of 7 outcomes. Now, first it says, what's the probability that True Colors wins the race? Well, that's the number of favorable outcomes divided by total outcomes, which is going to be 2 over 7. In B, it says, what are the odds in favor of True Colors winning the race? Well, this is the same ratio as odds against, except for it's reversed. And so it's the ratio of favorable to unfavorable outcomes, which is 2-5. And number 23, it says a standard die is rolled. Complete the following. What's the probability of rolling an odd number? Well, on a die, there's 3 odd numbers, 1, 3, and 5. So 3 out of 6, which does reduce to a half. What's the probability that you roll a 1? Well, that would be 1 in 6. There's one favorable outcome, that's rolling a 1, out of 6 total different outcomes. In C, what's the probability that you don't roll a 1? Well, there's 5 numbers on the die that are not a 1, so it'd be 5 out of 6. And again, we know that the probability that an event occurs plus the probability that it doesn't occur should equal 1. Notice B and C, they should add up to 1. The probability of rolling a 7, of course, that's impossible. That's 0. The probability of rolling an even number or a number less than 5. So this is an OR probability. The probability of getting an even or a number that's less than 5 is the probability of getting an even number plus the probability of getting a number less than 5 minus the probability that you get an even number and a number that's less than 5. So again, this is our general formula for finding an OR probability. Well, the probability of getting an even number is 3 in 6. The probability of getting a number less than 5, well, that would be 1 through 4, so 4 out of 6. The probability of getting an even number that's less than 5, well, that would be 2 and 4, and so that would be 2 out of 6. And so if you add those up, you get 5, 6. If 2 dice are rolled, what is the probability that 2 6s will be rolled? Well, each time you roll the die, it has no effect on the next roll, or the probability the next time you roll the die. So these are independent events. So the probability of getting a 6 and a 6 would be the probability of getting a 6 times the probability of getting a 6. And we're going to get 1 6 times 1 6, or 1 in 36. In G, it says find the odds against rolling a 3. Well, let's see. Odds against is the ratio of unfavorable to favorable outcomes. Notice there's 3 favorable outcomes when you roll a die if you're looking to get an odd, 1, 3, or 5. And there's 3 unfavorable outcomes, that's when you get an even number. And there's a total of 6 possible outcomes. So the odds against rolling a 3 would be 3 to 3 or 1 to 1 if you reduce. Just divide each number by 3. The odds in favor would be the reverse ratio, favorable to unfavorable outcomes, which is also going to be 1 to 1. All right, and that's the end of our first video for this test review.